Anyway, well, like I said, I'm not doing it right now in the whole process of anything. Anyway, welcome to those individuals who are joining us from home. I am recording today's discussion. Yeah. You're not going to need it today. You're not going to need it today. You need your notes, though. Oh, yeah. Not only will you need your notes, but you will need your calculator. I know. Isn't it awesome?
Does this look like a calculator? It looks like a calculator. I think that's a calculator.
All right. So it has been a minute since you can't even see that screen, can you? It has been a minute since we've taken notes in class. Okay, don't forget that stuff. The words that are in red are what you need to fill in the blanks with. We will be doing a few examples of some calculations. That's why you need to have your calculators out. When we do that, yes. Question? With that, you have one? You can borrow one. Make sure. Hand it in before. I also suggest that you put your name on your notes just in case you leave it behind anywhere, whether it be my class or someone else's class, that it'll get returned to its appropriate owner. Okay, so chapter 2, we are actually going to be discussing data analysis. In chapter 1, which I'm still grading the tests on, chapter 1 dealt with some kind of basic information. Now we're getting into, let's take that basic information and put it into what we can expect to see when we start doing labs again, okay? And that is when we start getting into calculations, certain units that we need to discuss, okay? So first thing we need to discuss are units themselves, okay? In the scientific community, this is probably one of the most important pieces that we can use, and those are called SI units. I do not speak French. Système International de Unités. I don't know. Basically just SI units. That seems a lot simpler, right? What they are an internationally agreed upon system of measurements. So really what SI units are, it establishes a common language in the scientific community. No matter where you are in the world, you can look at somebody else's calculations and understand what they're trying to show you, okay? It's only been around for what? 60 years. So it's a fairly new concept in the realm of science, okay? And so it initially was developed out of the metric system, you know, centimeters, millimeters, meters, everything like that. You know, those are all fine and dandy. And again, the metric system was designed in 1795. But we even see this today. It's still not used everywhere in the world. In fact, the United States is one of the last remaining countries who doesn't necessarily use the metric system as their main source of measurement. You see that a lot in terms of like your tools. If you ever, once you start getting into tools, you either have to have, you know, your millimeters or your inch sockets, or you know, whatever you're looking at. Okay, so in science, that's why it's nice to have the same units together. Now, over here on the right-hand side, table 2.1, these are very important to know. Okay, time is in seconds, length is in meters, mass is in kilograms, temperature is in Kelvin. We also see it in degrees Celsius, and we're actually going to be messing around with temperature today. Amount of substance is what we call a mole. We'll deal with that later on. And something that we don't necessarily do in here is electric current and luminous intensity, okay, where electric current is the ampere and luminous intensity is the candela, which, you know, we get it from candle. So those are the base units. It's a unit in a system of measurement that is based on an object or event. in the physical world. It is independent of other units. And as we just saw, that there are 7 SI base units. So as you're finishing this slide, I'm just going to kind of give you a heads up about what's going to schedule for the next week. Okay, but today is simply just going to be notes only. On Tuesday and Wednesday, I will be available on Google Meets. Okay, and you should hop on there because we're going to be doing some practice with density, which we're going to talk about here in a little bit, and temperature conversions. You will have an assignment for each one of those, okay? On Thursday, that is when we're going to have the homework for this section. We want to do some practice before we get into the actual homework. And then on a week from today, we'll get back into our notes and do section 2. So let's go through the 7 base units. The second, it's the base unit of time based on the frequency of microwave radiation given off by a cesium-133 atom. So in case you were ever wondering, as you right before you closed your eyes, where do we get the measurement for a second? Well, we measure the frequency of a microwave from a cesium-133 atom. So John, now you can sleep tight. Now that you know that. Okay?
Thanks.
You're welcome. Next, we have the meter. This is the SI base unit for length. Again, you're going to learn all sorts of interesting trivia today. The meter is based upon the distance that light travels in a vacuum in 299,792,458 of a second. So again, another bit of trivia. So I would say, based off of that light travels pretty fast. In fact, light travels 3.0 times 10 to the 8th meters per second. So that's quick. Again, the next one is the kilogram. It's got its units of kg. It's a base unit for mass. This is based on the terms of Planck's constant. Planck's constant, we start getting into, oh, no, I just completely blanked out. Planck's constant is going to be dealing with the atom and the electron. So it's an incredibly complicated aspect of Planck's constant is, but very useful. Does anybody ever watch Stranger Things?
Yeah.
Okay, so remember when I think it was in season 3 when Dustin and his girlfriend were singing that song?
I don't know, it was like 4 months ago.
Oh. Well, I watched it longer ago, and I'm older. You should remember this.
I watched a lot of movies.
Anyway, Planck's constant was a very important part or number that they needed to crack a code. And so that's all the reason I bring it up. So I love that show. Next for temperature is Kelvin with a capital K. That is the unit you're going to use. Base unit of temperature. 0 Kelvin is the point where there is virtually no particle motion or kinetic energy. Again, that's what temperature is. It's a measure of the kinetic energy that atoms possess. The point where there is absolutely no motion in atoms, there can be no visible measurement of temperature. Therefore, that is absolute 0. And this is equivalent to negative 273.15 degrees Celsius. That's pretty cool. Again, we didn't go through all of them, okay? But those are the ones that we will be discussing the majority of the time. Next, we have prefixes and base units. Everybody should have that packet that was handed out in the beginning of the year. Who did you come from? Hampton. He didn't hand you out a packet of like formulas and stuff like that? Okay. I will try to see if I've got a copy of it. If not, I will get you a copy of that math. And so, anyway, those of you who do have the packet, I do believe, have a breakdown of all of these prefixes. Okay. Anyway, prefixes and the base units. We use decimal systems with the metric system. It's based upon multiples or factors of 10, and it's used to convert between large and small SI units. Bless you. This will help better describe the range of possible measurements. Those prefixes have an equivalent value based on factors of 10. A kilo, it's 1,000 base units. It has a power equivalent of 10 to the third. So on and so forth. Okay. Again, the small numbers, you have negative powers of 10. Next, you have derived units, and this is what we're going to be working on when we have density. Okay, a derived unit is defined as a unit that is defined by a combination of these base units. Devin, you don't need your phone out right now. We're not calculating anything. An example of a derived unit would be speed. Okay, speed is calculated by meters per second. It combines two SI units, length and time. So meters divided by seconds, we can determine how fast an object is going. And what this does is allows for other quantities to be measured with SI base units. Density is another one, like I just mentioned, that we're going to be doing today. Okay. Density is mass divided by volume. We worked with the derived unit speed last semester in the physics part. Now we're going to be more focused on density of objects. The other units we're going to be looking at are volume and density. Okay, we already mentioned density. Let's talk about volume. It's defined as space occupied by an object. It is a derived SI unit measured in cubic meters, which is m cubed, or m to the third, or liters. 1 cubic meter is equal to 1 liter. That's something very important to know. 1 cubic meter is equal to 1 liter. In a similar fashion, you can also be measured in cubic centimeters, cm cubed, or milliliters. Now, cubic centimeters or milliliters, again, they are equal to each other, as we see in that line below. Okay, that is the more common unit of volume that we will be dealing with. Okay. Cubic centimeters will work well with solid objects with regular dimensions. Again, cubic centimeters works well with solid objects with regular dimensions, something that we can measure, say, using a ruler. Milliliters works well with liquids or solids with irregular shapes. If you are a solid with irregular shapes, oftentimes we will use what's called water displacement to help determine your volume. Next is a very important topic of density. It's defined as the ratio that compares the mass of an object to its volume. Simply put, the amount of mass per unit volume. Now, it itself, again, is a derived unit. It's measured in either grams per cubic centimeter or grams per milliliter. It all just depends on what is being measured. If it's a solid with regular dimensions, you're going to be using grams per centimeters cubed. If it's a liquid or a solid with irregular dimensions, you'll be using milliliters, grams per milliliters. Again, the equation for density is mass divided by volume. And each element or compound is going to have a unique density. And therefore, since all these substances have unique densities associated with them, density is a very common determination of unknown substances. If I were to give you a substance that you didn't know what its makeup was, you could calculate the density for it. And using sources that have tables with the information provided to you, you just have to look that up and you can identify what the substance is. So let's do a couple of density examples here. First, let's look at number 1. A sample of aluminum has a density of 13.5 grams and a volume of 5.0 cubic centimeters. What is the density of aluminum? So, nope, that's the wrong one. So you need a little lighter here. All right, so again, density is equal to mass divided by volume. So what do we know? We know that mass is going to be in grams, and which unit did they use? They used cubic centimeters. Okay, so centimeters cubed. Okay. So all we simply have to do, we don't have to rearrange anything for this. We just have to plug in our numbers. So density is equal to, again, I've already forgotten what the mass was, 13.5 grams. And the volume was, I believe, was at 5.0 cubic centimeters. Excuse me. So what is the overall density of this substance of aluminum? I'm asking because I don't have a calculator. Did you say 2.7? 2.7 grams per cubic centimeters. We use cubic centimeters for this case because it's a solid object with, we're assuming, regular dimensions because we were given this unit. So make sure you make sure what unit is being used in the problem. Let's look at number 2. Okay. A sample of aluminum is placed in a 25 milliliter graduated cylinder containing 10.5 milliliters of water. The level of water rises to 13.5 milliliters. What is the mass of aluminum sample? Okay. Again, we just established that density of aluminum was 2.7 grams per, again, first one we said grams per centimeters cubed, but since we're looking at placing it in water, we are replacing it with milliliters. So there's a few things that we need to think about, okay? First off, we're trying to solve for mass, okay? So I need to rearrange this formula to solve for mass. And I do so by multiplying both sides by volume. And so now I'm going to have mass is equal to density times volume. Before we get into putting our values in here, I like to go ahead and kind of organize my information. Again, mass is what we're trying to find. The density, we are told, is 2.7 grams per milliliter. Our volume is really the only question because we're not told directly what it is. So let's go back to the question. It says you have a graduated cylinder that already has 10.5 milliliters of water in it. You then place this piece of aluminum into the water, and we notice that the water rises to 13.5 milliliters. So we have to figure out what the volume of this aluminum is. And so we take the final volume listed, which was 13.5 milliliters, and subtract from that the original starting volume before we put the metal in there, which was 10.5 milliliters. I got those numbers correct, right? 13.5 and 10.5? Okay, thank you. So I go ahead and subtract. What I'm left with is 3.0 milliliters. And that's the volume I'm going to use. So once I've got my values for every variable I need, I go ahead and plug them in. Mass is equal to my density, which is 2.7 grams per milliliter, multiplied by my volume, 3.0 milliliters. And look what happens. What happens to the milliliters unit right here? It cancels out, which leaves us with the unit for grams, which is appropriate for mass. And so, double check my work here, but I believe we get 8.1 grams for our answer. Get 9.4, 9.5. It's just 3. 13.5 minus 10.5 is 3. Okay. Did you get 8.1? Okay. Good. So 8.1 grams. And that's your answer. Okay. Questions on density? Last few slides we're going to work on, take a look, are going to be temperature related. And this, what we're going to be working on today, is simply converting between Celsius and Kelvin. And that just involves addition and subtraction. Okay? So again, temperature is defined as a measure of how hot or cold an object is relative to other objects. This is a qualitative measurement. Okay? It is a qualitative measurement because you're essentially comparing two objects. We use a thermometer to measure. And typical units of temperature that we use in science is Celsius. And again, we get Celsius from the thermometer reading. And Kelvin, which is the SI unit. And again, we already mentioned for temperature that 0 Kelvin is essentially the point of absolute zero. There is no particle movement whatsoever. And absolute 0 Kelvin, so 0 K, is equal to negative 273.15 degrees Celsius. And as I mentioned, the process of converting between Celsius and Kelvin is very simple and straightforward. So, last slide here. Let's look at how we convert. So to convert from Kelvin to degrees Celsius, you are going to subtract 273.15 from Kelvin. So going from Kelvin to Celsius, you're going to be given the temperature in Kelvin. From that temperature in Kelvin, you subtract 273.15. You will then have your answer in Celsius. And the opposite is going to be true going from Celsius to Kelvin. You are going to add 273.15 to whatever temperature you have in degrees Celsius. So we've got two examples here. We've got negative 39 degrees Celsius to Kelvin, and then we've got 266 Kelvin to degrees Celsius. Okay. So we're going from Celsius to Kelvin here. What do I have to do? Celsius to Kelvin, what do I have to do? Very good. And so we get what? Say that again. Is it, are you putting a negative sign on 39? Anybody get anything different? 231. So we said 234.15. Yes, make sure you put that negative in front of that 39 there, and then add 273.15. You'll probably get a different number. Really? Plus. Let's see if he keeps going away. Negative, then okay, and then plus 273.15. All right, very good. So also, before we finalize this answer, it gets a unit capital K. Last one here, then we're going to call it a day. 226 Kelvin to Celsius. What do I have to do here? Subtract 273.15, and we get what? I think it's 7.15. Okay. Degrees Celsius.
It's a 66.
Is it 266? Thank you. I was like, that number doesn't seem right. Thank you. 266. That looks better on my end. My bad, everybody. Okay, so again, don't forget to put your unit. Now, before we close out for the day, on any homework that you have to do, like on a Google form or anything like that for like a homework or quiz or test, anytime you have to answer in terms of degrees Celsius, just put a capital C, because Google Forms isn't very friendly with subscripts and superscripts and everything and special characters so much. So all you have to do is just put a capital C for your final answer. Okay? So again, on Tuesday, make sure you hop onto the Google Meet if you are at home. And then we'll continue doing some work with this stuff in the first section. Those of you at home, thank you for joining. You may sign off now. There is no homework. I'm going to stop the recording.